Hello and welcome to today's webinar. My name is Jacqueline Dorsey of Lean Frontiers and I'll serve as your host today. I'm excited to bring to you today a short webinar on lean product development facilitated by Durwood Sobek. He is a professor and program coordinator of Industrial Management Systems Engineering at Montana State University and has co-authored a Shingo Prize-winning book. I have a couple of notes before we begin. Due to our limited time, we will not be doing a Q&A session. Also, this will be recorded if you want to refer back to it later. So for now, let me turn things over to Durwood.
Great, thank you, Jacqueline. And welcome to this webinar on set-based innovation. As Jackie mentioned, I am a professor at Montana State University and program coordinator of Industrial Management Systems Engineering. I've been doing research in lean product development for almost 2 decades now, and it's been a really exciting journey, and I'm really excited to share with you a little bit about this topic. Some of you may know that we came out with the 2nd edition of Alan Ward's Lean Product and Process Development book, and you can always find more details about set-based innovation and other lean product and process development topics in that book. Thought I might start with a situation that you might find familiar. Perhaps there's been a issue that's popped up in production and that produces a lot of excitement in the organization and a lot of firefighting, and management, of course, wants to stay on top of what's going on. And so what they would like to do is get reports on how things are going. Of course, when that happens, that means that the team or the team lead has to take time out of their day to prepare the report and then actually conduct the report. And of course, that means less time for development work, which can then produce more issues that are overlooked and more firefighting. And if that continues, oftentimes management wants a greater frequency of reports, which means less time for development work. And if that continues, then we can end up in quite a vicious cycle. If that doesn't sound familiar to you, then maybe something like this, where we have a failure in prototype testing, and a project that was on time yesterday is now 3 months behind today. And of course, our management wants to be helpful, and so when they see the schedule slip, perhaps they want to add some resources to the team to help get things back on schedule. Well, of course, whenever you add more resources, that requires additional coordination on the team. That means less time for development work, and even though the team is bigger, you might actually find that the schedule still continues to slip. And if we continue along that path, of course, we can end up in another vicious cycle. And of course, where do those resources come from? Well, they come from the next project, which means that project starts behind. So the question I have to these scenarios is, do these responses really address the root causes of what's going on? And as you ponder that question, let me add a comment to say, well, if they are, then why are these recurring themes in many companies? So I would suggest that if it's a recurring theme, then we probably haven't got to the root cause of the problem. One of the things that oftentimes precipitates or is behind the scenes in these loops, in these vicious cycles, are what we call loopbacks. And a loopback is any time that we are redoing development work that's been completed earlier in the project. And that usually means we're revisiting a decision that was made in light of additional information that has come to the attention of the team. So in the prototype test failure situation there, we went in with a certain decision and then we were surprised by the results, and so we're going to have to redo some development work, some design work, some engineering analysis work to bring that design in compliance with our design requirements. So that's a loopback, and one thing that we have seen is that there does seem to be quite a bit of developer time spent on loopbacks. In fact, some of the companies we talk to, the number can get quite large. Some might estimate 30, 40% of time. We've had others that have estimated that it might be as much as 3/4 of development time of a developer's time is spent redoing work that they had already done previously. In other words, they're spending a lot of their time in these loopbacks. So why do they occur? And there might be lots of reasons why they occur, but a lot of those reasons come back to sort of a basic idea that you learn something later that you didn't know earlier, and had you known that information, you probably would have done things differently. So fundamentally, loopbacks occur because of a lack of knowledge. If we can get that knowledge earlier in the process, then hopefully we can make better decisions that we don't have to revisit later in the project. So let's talk a little bit about the, I guess, theory behind why we might think this way. Most would agree that the cost of looking at a new alternative increases as you go through the project. So early in the project, when you're dealing with sketches on the back of a napkin or on a whiteboard, to explore a new idea is really the marginal cost for a new idea is very, very small. Then as we get into developing CAD models and 3D solid models, we start adding detail to those ideas, and to make a change is a little bit more expensive than just the sketches. And then certainly as we get into prototyping, to look at particularly some of the more high fidelity types of prototypes that we would do life cycle testing on, for example, those can get quite expensive. And then the most expensive of all would be trying to look at a new idea when we're already in production, such as trying to deal with a production issue, yield issue, or warranty problem. And most would agree that not only does the cost to look at a new alternative increase over the life of the project, it actually increases in a geometric fashion, like the curve that you see on the screen there. And you can put your own function there, but for your own company or industry. But a lot of folks would say, you know what, each phase there's sort of a 10-fold increase in the cost of looking at a new idea, or the cost of making a change. So researchers in product development have studied engineering changes in product development, and what they find is that there seems to be a lot more changes later in the development cycle than earlier. And this is sort of a little bit counterintuitive if you put it on the if you map it on the cost of learning curve, because it looks like we're investigating new ideas when it's pretty expensive to do that. Wouldn't it be better to front load the project so that you look at lots of ideas early on, where it's relatively inexpensive to do that investigation of new ideas, so that when you get into those later phases, you're not having to make so many changes? A different perspective, rather than looking at the cost of development, is what some have called the designer's dilemma. And this is a phenomenon that we're all familiar with. If you've ever got to the end of a project and said, wow, if I knew then what I know now, boy, I would have done things differently. And if you've said that, you've experienced the designer's dilemma. And the designer's dilemma is simply this, that early on in the project, you have all the freedom in the world to do whatever you want as far as proposing solutions and so forth, but unfortunately you have the least amount of knowledge that you will during the life of this project. And then as you make decisions and you move forward with the development or the design process, your design freedom actually decreases over time, because every decision you make constrains what you can do next. But you're also learning, so your knowledge is increasing over time. But unfortunately, by the time you hit near the end of the project, you have the most knowledge, but the least amount of freedom to be able to actually use that knowledge. So that's the designer's dilemma. So if we look at that engineering change order pattern that we saw before, again, it seems like it wouldn't be the wisest thing to be trying to make changes late in our process, because that's when, at a point in the design process where we've made the most decisions, and therefore we've added a lot of constraint and we have the least amount of design freedom. Wouldn't it make more sense to do that exploration at a point where we have the most design freedom and kind of follow that same curve down? If we do that, then we also have the opportunity to actually change the curvature of that knowledge growth curve so that we learn rapidly early in the process and can then make, hopefully, wiser and better choices. So just to recap, loopbacks are a pretty big source of waste in product development organizations, and oftentimes the common management responses do not address the root causes of the loopbacks. And as we saw in a couple of those negatively reinforcing cycles, they can actually make the situation worse because they're not addressing the root causes and they actually produce other problems besides the loopbacks. Fundamentally, a lot of loopbacks occur due to a lack of knowledge. Not all of them. You can probably come up with some examples where it's not, but oftentimes if we ask why enough, we get back to, you know what, we just didn't know that, and that's what got us in the end. And hopefully you agree that it makes economic and logical sense to invest in knowledge early in a project so that you can front load that project up and make better decisions early and therefore not have to try to make changes late in the process. In other words, try to avoid those loopbacks. So the question then, by way of introduction, is how can we front load product development projects? Now, if you poke around the literature, you can find a number of different answers about team staffing and team resourcing and different things like that. And those are all good things. But what I would like to focus in on is how you can use step-based innovation to help you front load a development project. So that's what we're going to talk about today. So I thought it would be interesting for us to go at this by talking about a very famous example of a development project, the Wright brothers, and designing the first airplane. Of course, this is a real challenge if you're back at the turn of the 19th century, or near the end of the 19th century, I should say, because if you're testing a prototype, it's a pretty dangerous endeavor. In fact, if the prototype fails, then your life is endangered. There are a lot of people at that time trying to be the first to invent heavier than air powered flight. So here's some examples on the screen. There's Otto Lilienthal from Germany, who tried for 10 years with 2,000 test flights over that 10-year period. Unfortunately, he died in one of his flights in 1896 and never did succeed. There's a fellow in France, a Frenchman, Clement Ader, spent quite a bit of money over a 25-year period and never did achieve that holy grail of powered flight. In England, Hiram Maxim, the inventor of the machine gun, also invested a large sum of money and still didn't succeed. And here in the U.S., Samuel Langley was awarded by the U.S. government $70,000 to work on developing the first aircraft, and he spent over 16 years, and he never did achieve a manned flight that lasted for longer than a few seconds. That few seconds was the amount of time to launch a glider over the Hudson River. He had a contraption set up where he would launch gliders off a launch boat over the Hudson River, and they could stay up in the air for a few seconds till they crashed into the river. Well, how about the Wright brothers? Well, the Wright brothers are really interesting because they actually don't have university degrees, never did. They spent a fraction of the money. They didn't have a lot of resources. In fact, this was a hobby of theirs. They ran a bicycle shop for their main income. So they only had a couple of people, and they had to spread their development out over fits and different fits and spurts of development work. And here's the interesting thing. Their first full prototype flew. In other words, they didn't have any loopbacks. So you might be asking yourself, wow, that's quite a difference. How did they do that? Well, you can read a lot about what the Wright brothers did and didn't do, but here's, from my perspective, they actually innovated an entirely different approach. So one of the things that they did is they first identified that they had some knowledge gaps, and 3 are documented in their journals. In-flight control, wing design, and propulsion. The first one that they ended up tackling, I'm not sure that it was intentional that it was this one first, but it was the one that they tackled first, was how do we get in-flight control? And they were able to do some systematic testing on what you might consider to be subsystem prototypes, right? Gliders or kites. And they came up with a couple of different ways that they could do that control. You have the diagram there showing that. One of the things that they discovered as they were towing one of their kites behind is that they needed to control for yaw. They had roll and what's the other one? Tilt? No. Sorry, you got 2 of the axes, but they didn't account for yaw, and so that was one thing that they had to do. The other thing that they did is they discovered that the existing lift tables that were used for wing design and that Samuel Langley was using were actually incorrect. Every wing that they designed using those tables didn't work, and rather than blaming themselves, they blamed the lift tables and said, you know what, we need to corroborate these findings. So they moved from flying kites to the wind tunnel, which they're pretty famous for, and they developed a lift balance there to evaluate different wind foils. And they actually ended up testing a bunch of different airfoils for lift and drag. And they recorded those data in their journals in the form of the curves that you see on your screen. After they had tested dozens of those airfoils, and they had a good idea of what lift and drag should be like, they built a subsystem glider. It's not powered. There's no power on this. They're just testing the wing design now, and they can also see evidence of their latest iteration of the in-flight control. And they floated this glider, and you can see one of the Wright brothers there chasing his glider down the sand dunes at Kitty Hawk. To close the propulsion gap, they had a breakthrough realization, and that is that a propeller is really just a wing turned on its side and rotating rather than stationary. And if that was the case, then they could use the existing airfoil curves to design a pretty efficient propeller. So they did that, and you can see the replica of the original propeller that they used, which is still, by the way, very efficient even by today's standards. And you can see that the cross-section of the propeller changes as you move from the rotating hub out to the tip of the wing. And that's because you have different air velocities at different points along the way, and therefore the most efficient airfoil is going to be different. The nice thing about that is that this highly efficient propeller allowed for a much smaller motor, which of course weighs much less and would be much easier then to design a wing to support that lighter load. So they had closed the propulsion gap with that wind tunnel data. So now with all the knowledge gaps closed, they designed and built a full system prototype that they transported down to Kitty Hawk, and they actually flew this aircraft that you see there. The first test flight actually crashed, but that was due to pilot error. And once they had fixed their plane, they repaired it. And while they were repairing it, actually, one of the brothers sent a telegram to their father and explained, just giving an update on progress, that they had crashed the aircraft, but success was assured because they knew that the aircraft was going to work. It was just due to pilot error that it didn't fly. And so they made the repairs, and then it flew the maiden voyage, and that's the one that's in the history books. So the thing that's really amazing to me is that their first prototype flew, and they didn't have to actually redesign that prototype, at least in terms of the functionality that they were looking to achieve. So that brings us, by way of introduction, to actually the first principle of set-based innovation. And that's this idea of developing knowledge or trade-off curves that inform you about the design space, so that when you actually get down to designing the thing, you know where you're at. You know that you're in that feasible region, and you can be assured of success as you move into the later stages of your development process. If we look at the Wright brothers, we can see that they turned the development logic on its head. Rather than doing the old design, build, test, or design, simulate, test, or design, analyze, design, build, test, and then redesign, right? So design, analyze, redesign. They actually went the other way. They said, you know what, we have a basic idea of how we want to do this, but let's test at the subsystem level lots of ideas. Let's characterize our design space with respect to how these different parameters affect the functional performance of our design. And once we understand those relationships, then we can come up with a good design. And when we do that, then the knowledge that we create there is useful not only for this project, but for all future projects. In fact, those basic airfoil curves have been built upon by the predecessor of NASA, the NACA. Airfoil curves are still used today to help design that, to help design aircraft wings, because they're based in the fundamental physics. Ron Marsilio at Teledyne Benthos shares a story about how his development group was working on a new bottle inspection machine, and they worked very hard to develop trade-off curves before they sat down and did the detailed design work. And here's an example of one of them that they used. They had developed, I think, a couple of dozen around different parameters of their concept. And when they sat down to do the detailed design, it went very quickly. They didn't have any trouble in production. They didn't have any trouble at the beta test sites, and they produced a machine that became a real money winner for their company, because they had that opportunity to really understand where they needed to be in the design space, and then they could do the detailed design very rapidly. You don't have to necessarily generate new data. Sometimes you can use historical data, as in this example here, where this company had pulled data from historical designs, die tryout data, and they were able to map out a couple of different parameters. And when they discovered that the designs that have good manufacturability were in one portion of the design space, and the others that had poor manufacturability were in the other part of the design space, they could come up with a pretty easy way for them to test the manufacturability. This is the design limits of our manufacturing system as it stands right now. And as long as you stay on the one side of the curve, we can guarantee, at least on this particular dimension, that you're going to probably have a manufacturable product. The second principle of set-based innovation is what I've called here parallel convergence. To explain this concept, I'm going to go back to sort of the conventional way of thinking about the design process, and that's one of basically an iterative mindset as opposed to a convergent mindset. And in this case, what happens is that, of course, we all want to generate lots of ideas for solving a given problem, but typically what will happen is we'll evaluate that in a preliminary way and choose what we think is the best or most promising alternative. We'll work on that alternative, add some detail to it, analyze it, look for ways that we can improve it, and we just go through that iteration process until we have met our design requirements. One way to characterize that is that you're moving from point to point in the design space. So each iteration is a different point in the design space. So we call that a point-to-point search for the solution. And if you use that in your companies, then it can cause all kinds of problems because it's really difficult to know when you actually converge. And it's really difficult to know where to go next. And oftentimes, you don't really produce knowledge that's useful for another project because unless you want to go backwards through your design process, it doesn't really provide you with very much knowledge that you can go forward. And a big issue is that it's really difficult for teams to work concurrently because the process is pretty unpredictable, and a change in one part of the system can precipitate changes elsewhere. In contrast to that, we might look at a situation that looks like this, where rather than communicating my best idea, we communicate a set of alternatives, and we compare that with a space of alternatives on the other side. Now, this case, we're looking at product design versus manufacturing, but they could be any two interfacing subsystems. So if we can identify that intersection and then go through our process of development elimination by staying within that identified intersection, then we have a process that becomes quite reliable, and it allows both sides to then work concurrently, adding increasing detail as they work their way through the development process. So an example of that would be in automotive development. A lot of times the styling group will have a process that's very convergent, and rather than trying to pick an early winner from their initial set of alternatives, they will either choose a set, or what I like to suggest is eliminate those that don't work and carry forward those that are still promising. When they do that, then they increase the level of fidelity. They don't run all the way to fully realized CAD model. They just take it to the next stage of development where they can do further evaluation and further elimination and so forth until they converge to a final design. Now, in parallel with that, the engineering group is also looking at those alternatives, and they're doing, in the early stages, some design studies. They don't do complete engineering analysis, but they focus in on areas that look like they might be problematic, and they look at alternatives from an engineering standpoint, how they could support that styling alternative, and they run their design studies, and that information then is used in that elimination process, so that you're not making the convergence process is not done from just one perspective, but it's done from more of a systems perspective. So in other words, it looks kind of like this, where we have both groups converging in parallel, sharing information back and forth so that it informs the development of the other, and we can look for what would be compatible designs so that when we finally converge, we don't have to loop back. The Ford Motor Company, in their recent transformation, instituted what they call the Kinto phase. Kinto is borrowed from Japanese, it just means study, where they study multiple alternatives in this early phase in order to identify the pluses and minuses and compatibility with other subsystems in order to make their elimination decisions. And this produced a great deal of efficiency and effectiveness in their development process. Here's just another picture of looking at that, where if you're looking at different, just kind of a Venn diagram of alternatives, and you're really looking for where's that overlap in the different possibilities and alternatives in terms of where you're going to find your acceptable designs. One thing that's really helpful in this convergence process is if you can have some flexibility in your initial specifications. Again, similar to that knowledge curve, it's very difficult, I think, to set your specifications early in the project because you have the least amount of knowledge at that point. So if you can have a little bit of flexibility through target specifications, and then after you understand the trade-off space, you can narrow in on exactly what the specifications that you want, that can really help speed up your design process and allow you to balance the trade-offs to maximize the overall system performance. So that might look a little bit like this with any given specification, that you might start with a desired and a minimum acceptable requirement, and then as you learn more, you gradually narrow in on what that final specification would be. All right, so then our final principle that we're going to talk about today, a step-based innovation, is feasibility before commitment. So you may be asking yourself, well, how do I manage that convergence process? Well, one way to do that is to really focus in on these knowledge gaps. And if you're able to develop trade-off or limit curves or knowledge curves, you can close those gaps by really understanding those trade-offs. So that can help you decide what alternatives to eliminate or where to focus your design efforts. If you're using discrete sets, like in the parallel convergence, you'll want to try to aggressively eliminate alternatives. So rather than trying to pick a winner, essentially you just look for the weakest link, and that way you can eliminate it. And you don't need to run everything through the same test. Look for that Achilles heel and try to be creative in how you can get the information you need in order to make a decision at that level. You don't always need the highest fidelity model. Sometimes a lower fidelity model that you can generate quickly will generate enough information for you to decide whether to keep it in the set or not. You want to gradually narrow those. Doesn't mean you have to go slowly, but you'll want to give enough time for other people to react to your set, and also to make sure that you've got a known feasible. Because if you have narrowed your set to the point where you're not sure that you have a known feasible, then you've probably narrowed too quickly. So again, what you can use for the convergence process is design reviews. And you don't need to converge every subsystem at the same rate, but it will allow you through these design reviews to determine, do we have knowledge gaps open? What knowledge gaps do we have? What's a quick way for us to eliminate that knowledge gap, put together an action plan, then hopefully you'll have a cadence of these design reviews. So the next week or in 2 weeks, whatever the time frame is, you come back with whatever information you have, you can make an assessment and go that way. And only add granularity as it makes sense. Try to avoid going to detailed design too quickly, because if you end up going to detailed design, detailed analysis too early and redoing it, then again, you're caught yourself in a loop back. If you can make your progress visible, that's really, really helpful. So one of the things that you're doing as you're evaluating the alternatives in your set is try to make sure that you have compatibility. So try to ensure that compatibility before you worry about getting the design too terribly complete. Because if you spend a lot of time detailing out a design only to find out later that it's not compatible with someone else, you're going to get yourself into another loop back. And again, you're producing a lot of waste there. So really focus in on compatibility in those earlier phases and use that as part of your elimination process, so that when you get down to deciding you're going to do detailed design and move towards release, you have a much higher degree of confidence that that alternative is going to work for you. Once you've narrowed, you want to do everything you can to stay within the set. So make sure that you do your homework to ensure good decisions through cross-functional design reviews, comparison against design standards, and doing double check. And also try not to specify more than you need to avoid over-constraining your design space. Here's a quick thought problem as we wind down here. Let's suppose that you have 5 subsystems in your next product, and each subsystem team is pursuing an innovative design with an 80% probability of success. What is your chances of the whole product being a success? Well, if you run the probabilities, you know that it'd be 0.8 to the 5. In other words, you've got a 33% chance of success. And that's not very good, is it? So let's switch this around a little bit. Let's say that we pursue a backup alternative along with the innovative one. And we set a cutoff date that says, if the innovative idea hasn't panned out by such and such a date, we revert to the backup idea. What is your probability of success then? Well, it jumps up, right? Because now, since you can always revert back to the reserve idea, the backup idea, now you have a 100% chance of product success, and at the same time, odds are good that you'll end up with 4 of those 5 innovations. So this idea of this gradual narrowing and keeping a backup solution can be really, really powerful in your development processes. Okay, so far today we've talked about 3 principles of set-based innovation. The first one is really understanding the trade-off space and how the design parameters affect your functional performance, and do that in terms of trade-off or knowledge curves. The second idea is this idea of parallel convergence, where rather than trying to pick a winner and iterating our way to a good solution, we look at sets of ideas and we eliminate the weak alternatives and the ones that are incompatible with other subsystems so that we can converge on a solution that works for all. And finally, we want to make sure that before we're committed to an idea that we've actually established feasibility, both in terms of functional feasibility, but also manufacturability and compatibility with other subsystems. If you apply these set-based principles, you'll be able to move the learning earlier in the design cycle where it's relatively inexpensive for you to learn, and therefore you can decrease the cost and increase the productivity of your development teams. And also you can change the knowledge growth curve because you're generating much more knowledge early in the project rather than later in the project. And if you are forward thinking, you can actually couch that knowledge in such a way that you can reuse it on future projects. Well, that's all we have time for today. I hope this webinar was informative and helpful to you. If you would like to share your stories of set-based principles and applying them in your company, I would love to hear about them. So there's my email address, and if you have any questions, I would be happy to take those by email as well. So at this point, I'll turn it over to Jacqueline to conclude our webinar.
All right. Well, thank you, Dorwood, for facilitating our session today. Before I close, I just wanted to go over a couple things. The first one is that his presentation is available as a handout. If you look on the right side of your screen, there should be a Handouts tab that you can click on to download that so you can view it. Another thing I wanted to let you all know about is we are launching a new Lightwise webinar series for 2016, and we want you to be the first to know about what's coming. So if you visit www.lightwise.me and submit your name, you can find out what's going on there. So to wrap things up for today, I want to remind you that this webinar is being recorded. So look for an email following our time together for a link to the recording. And feel free to share this throughout your organization. So again, thank you, Durwood, and thanks to each of you for participating in today's session. Goodbye.